Welcome, everyone. For today's prep, we're going to start looking at partial fractions. And this is an algebraic technique that allows us to kind of simplify rational functions into something that's easier to integrate. So the example we're going to be looking at is this situation right here. This is one we're actually going to calculate in a few minutes. So on the left here, this is a rational function. It's a polynomial divided by another polynomial. And as it's written, if we wanted to integrate this thing, this would be pretty difficult in its current form. What partial fractions is going to do is it's going to break this up into kind of separate, easier terms that we can integrate on their own. So this algebraic technique of doing partial fractions is going to take this rational function, which is difficult to integrate, and it's going to split it up into these easier fractions that we can work with. So let's see how to do this. And the first step of this process is when we're presented with a function is to do the partial fraction decomposition. And there's a whole bunch of, well, not a whole bunch. There's 4 situations we're going to run into based on the terms in our denominator. So we might have a linear term like this, where the highest power on x is just a 1. And we might have a linear term where, again, the highest power on x is a 1, but then this whole thing is raised to some power n. So we say that this is a linear term with multiplicity n. We might have an irreducible quadratic term, so something that can't be factored in our denominator. So the highest power there is x squared. Or we might have an irreducible quadratic that's repeated, so it's raised to the power n. So we say that it's an irreducible quadratic with multiplicity n. Today, in this prep video, we're just looking at the linear term with multiplicity 1. So our first step is to make sure our denominator is factored. And once we've factored the denominator, each of these linear terms in our denominator is going to give us a fraction of this form. So a over that linear term. So we'll see in a second how this looks. So a is going to be a constant. So let's try out. Let's look at example 1. We're just going to do the first one here. This is the example we're going to work with. So the function here is 2x plus 5 over x minus 1 times 3x plus 4. Denominator's already factored for us. So the partial fraction decomposition for this, basically each factor in our denominator is going to get its own fraction. So that x minus 1 is going to get its own fraction. And then the 3x plus 4 is going to get its own little fraction. Now we don't want to use a again because a is already used in the first fraction, so we'll just use b. Or if you want, you could use like a sub 1 and then a sub 2. Perfectly fine to do that. But for the ones we're going to be working with, you're not going to have too many terms. So just kind of going down the alphabet works just as nice. All right, so this is called the partial fraction decomposition. So basically each linear term in our denominator results in a separate fraction here. So the next step of this is to actually figure out these constants a and b. So let's jump down to example 2. This is where we're going to actually do our work. All right, so let's go through this process. How do we do the partial fraction decomposition of a rational function like this? Well, the first step, and in this case it's already done, is we want to factor the denominator. All right, so that one done for us here. Second step, we want to write out our partial fraction decomposition. So let's write out our decomposition. So in our case, we just did that. The function was 2x plus 5 over x minus 1 times 3x plus 4. And again, each of those linear terms gets its own fraction. So a over x minus 1 plus b over 3x plus 4. All right, so we want to get our decomposition there. And then the next step is, well, we got to figure out a and b. So we need to find these coefficients. And the way we can do this, the first step of finding the coefficients is we can multiply both sides of this equation here, of our decomposition, by the denominator. So our first step is to multiply the left-hand side by our denominator and to multiply the entire right-hand side by our denominator. And this is going to give us just an easier equation that we can use to solve for a and b. So when we do this on the left, the x minus 1 here is going to cancel the x minus 1 there, and the 3x plus 4 is going to cancel out the 3x plus 4. So we get a lot of nice canceling. So when we do that, we end up with just a... And I want to get rid of those cross-outs. There we go. All right, so then we have just the 2x plus 5. And then what's happening over there on the right-hand side? Well, we're going to distribute. So we're going to take this entire x minus 1 times 3x plus 4, and we're going to distribute it individually to each fraction. So this whole thing is going to go to our first fraction there. And when we do that, the x minus 1s are going to cancel. So we end up with a times 3x plus 4, the opposite term. And then when we distribute, again, this whole thing to the second fraction, well, in this case, the 3x plus 4 is going to cancel out the 3x plus 4 there. So those are going to cancel. And we're left with just b times x minus 1. So we're left with, like, the opposite term there. All right. So now we can go about this a few different ways once we get down to this equation. So I like just plugging in different x values. So in our case, when you have a linear term like x minus 1, we can just plug in x equals 1 into this equation, and that'll give us an easy equation to solve for either a or b. So if we plug x equals 1 in, why am I choosing x equals 1? Because when if I set this equal to 0 and solve for x, I get x equal to 1. So when I plug 1 into this, I'm going to get a big 0. So that's going to make this whole thing 0 here. So when I plug 1 in, on the left-hand side, I get 2 plus 5, so I get 7. And then on the right-hand side, I get a, I don't know what a is. And when I plug 1 in for x here, I get 3 plus 4, which is 7. And again, when I plug 1 into here, I get 0. So I get b times 0. So 0. So the resulting equation when I plug x equals 1 into this is just this equation right here. And this is easy to solve for a. I just divide both sides by 7, and I get a is equal to 1. All right, so then we can do the same thing or a similar thing for the other linear term. Now this one isn't as nice. I could choose negative 4 over 3. And maybe I'll do that. But just so you could choose negative 4 over 3, and that would give you a 0 here. And then you could solve for b. But I always like 0. Let's plug 0 in. So if we plug 0 in, what are we going to get? Well, if I plug 0 onto the left-hand side, I get 2 times 0, which is 0, so I just end up with a 5. And then when I plug 0 in here, I'm going to have 4 times a, so I'm going to have 4a. And then when I plug 0 in here, I'm going to have negative 1, so I'll have a negative 1 times b, so I'll have a minus b. And since we already know what a is, I can fill that in here. And if I solve for b, I get that b is equal to -1. So I can subtract 4 from both sides, or really I could add b to the other side and then subtract 5. So I get b is equal to -1. And now that I know my two fractions, or my two constants here, my two coefficients, then the last step is, well, put it all together. And that's precisely what we've done right here. So instead of a over x minus 1, I filled in what my a value was. It was 1. And instead of plus b over the 3x minus 4, I filled in what my b value was. It was -1. So you just want to make sure you fill in the constants then once you find them. Write down the final answer. So this is going to be one of our strategies of how to find the coefficients. Probably the one I like the best. Just plugging in some easy to evaluate x values. So we'll see. There are other strategies on how to do this. So how to find these coefficients. I like plugging in the x values. So especially when we have linear terms, you can always try, just some nice easy ones like 1 or 0 or -1. But another technique, and maybe we'll try this in an example in class, is to compare the coefficients. So there are multiple ways to do these things. So we'll try another example in class just to get practice with this, but this is essentially the idea. And when we get to it, what we're going to be seeing in our next learning outcome is once we do the partial fractions, how can we integrate this? And, just a couple U subs here. All right, so that'll do it for today. And in class, I'm just going to be practicing a few more of these. Bye-bye.